All right, here we go. Okay, mean value theorem is considered by some to be the most important theorem. I think it's not. It's what some say.
Agree to disagree.
I agree. All right, so, but remember we have very few, we have a lot of theory, but we have very few like formal theorems. This is one that you would be expected to know. The mean value theorem for derivatives, okay? Now, it should look vaguely familiar on either side, okay? The mean value theorem for derivatives, f of x, of course, again, is continuous on a closed interval, okay? And differentiable on the open interval, okay? So there's no corners like that absolute value, God bless you. There's no corners, there's no cost, there's no discontinuity. We already said that piece. Okay, and that's pretty standard for most of our theorems. Continuous on the closed interval, differentiable on the open, okay? There's at least one value C in the interval AB such that, what does that mean, f prime of C? That is the derivative, sorry, at C, or the slope of the tangent line at C, right? And what does this look like to you? Recognize that? That looks like the regular slope, which is the secant slope. We've always also called it the average slope. Okay? So basically the mean value theorem, mean usually means middle. It doesn't mean exactly middle, just in the middle somewhere in between. There is a point that we're saying, all right, I know here's my C. At this point, this line and this line have the same slope. See, equal. The slope of the tangent line is equal to the slope of the secant line. And usually our job is to figure out what that C value is. Okay, and that's the mean value theorem. So we can figure out the slope, just like we always can. At a certain point, we know it's some kind of function. So it'll have an x in it. We can replace it with C if we want. And then we can figure out all this. We set them equal to each other, and we find that value, C, which is really an x value.
What's the significance of that? Because like blue is
the red line is
tangent.
secant.
Oh, I thought you said. I thought
This is the secant line. Secant line on AB. Okay, the purple is the tangent line.
So they have the same slope because they're parallel at some point.
Yes.
Is that why?
Yes, that's fine. All right. So let's try an example of what they're going to do with this. Okay, this is the words that it means that average rate of change. The mean value theorem connects the average rate of change, which is the f of b minus f of a over b minus a, with the instantaneous rate of change, which is the interval, which is the derivative, right? The secant line through the points and the tangent line have equal slopes and are therefore parallel. Okay? All right. So let's figure out at what x value on -2 to 3. I did you a graph there. Does f of x equals x squared plus 2x minus 1, so that's this graph right here, satisfy the mean value theorem. So that's kind of what they say, satisfy the mean value theorem. So first of all, you kind of have to run through, is f of x continuous? And remember, it only has to be continuous on the interval. Of course, this function is continuous everywhere, right? Okay, so we don't have to worry about that. So check. All right. Is it differentiable on the open interval? Of course, you can look at it. It's a quadratic. Is there going to be any sharp points, cusps, Discontinuity? No, so it is check, it is differentiable. All right, so therefore, somewhere f prime at x equals f of b minus f of a over b minus a. This is technically how we remember the mean value theorem. That's the kind of formula that we say, oh, that's what we need to do. Okay? If you look, move these around a little bit. They had C in its place, C and X. Remember, C is just a special X value. You can memorize in either way, and you should be good. Okay? All right, in this case, I'm going to go back to single here. In this case, A and B are that interval. Okay, of course, this is f of x. All right, so we're going to plug in this formula. Okay, f of b, I guess A is -2, and B is 3. Okay, if that's really messy for you, just rewrite it. All right, so f of 3, I clipped the table for you. What's f of 3? 16. And you're just plugging in 3. If you didn't have the table, you could say 3 squared plus 2 times 3 minus 1. It's not a big deal. Okay, what's the f of -2? What is it? 1. And again, it's -2 squared plus 2 times -2 minus 1. 4 plus 4 minus 1 equals -1. That's where that number comes from. Okay, but it's a -1, right? Wait, what's going on?
Is it 16? Oh, never mind. I used
9 plus 6 minus 1.
No, 9 15 minus 1 is 4. Yeah, it's 14. You also put it in the calculators plus 1 and minus.
Okay, we'll just switch it then. Does that work? Yeah, because then that one works too.
Yeah.
Okay, sorry about that. That's weird. Okay, so then that would work with that too. Right, -1? Okay, well, good. I'm glad y'all are checking that. Okay, so 16 minus 1, remember it's f of b minus f of a. It's just that regular slope formula. And then 3 minus a -2 is 5. Okay, so this is 15 over 5, which is 3. Okay, be careful. You're going to kind of keep this intact here. All right, what's f prime of x? There's f of x. 2x plus 2. That's right, just the regular, however you find f prime. So 2x plus 2 is now equal to 3. So we do what we got to do to solve for x. 2x equals 1, x equals. Okay, so what does this mean? It means on your graph, here's x equals 1/2 ish. There's a tangent there. Okay, that is parallel to that one. That looks pretty good, right? So this is your secant line. Okay, this is your tangent line. You have the same slope for those. That's why they look parallel. They should totally look parallel. Okay. I don't know why that's so important.
It's the most important thing we will.
Some say, you know,
It seemed like all that
it has a very
was out.
specific application, so how important could it be? You know?
Yeah.
But it is one of those things that you're going to get asked. And what happens, I guess why they say it's important is because it's kind of bridging the average rate with the instantaneous rate. There's some point where they're the same. The average rate and the instantaneous rate. Okay? Because if we even moved up slightly to maybe right here, now let's do a tangent at that point. Yikes. It's not really parallel anymore, is it?
No.
Okay, not at all. So, unless, of course, that's your no. Okay. What'd you say, Madeline?
I said,
Yeah. Yes. Okay. So that's what they're going to ask you. That's really all they can do with the MBT. It's very specific, so it's not a big deal, but it is if you don't remember. So when you think about the MBT, think about this right here in terms of A and B. Okay. This is just kind of a thought. You don't have to express it in the terms. They may ask you, is the mean that if they say no, it doesn't have a point, you might have to explain why, and then you'd say, well, because it's not continuous, so it's not guaranteed, or it's not differentiable, yada, yada, yada. If it's not differentiable, remember this is going to be a problem. So that's why that's in there.
we just found the point where
You found the point at 1/2 here where the tangent line slope at that point is going to be parallel to, the tangent line is going to be parallel to the secant line on a particular interval here.
So 1/2 is not the actual slope value. It's
No,
the point where
1/2 is not the slope value, right? We can figure out the slope value. How would we do that? Right, so we did that already once, right? At 1/2, what is the slope?
Three.
So we take 2 times 1/2 plus 2, should be 3. And,
You just know that, yeah.
yeah, we just knew that too because remember they were saying as that. Okay, so anyway, just different ways to go around finding it, confirming it, I suppose, more than anything. Okay, all right. Now this next piece is you've heard some of it before. Okay, and some of it you haven't. We're going to go into a little bit more detail. We did this chapter when we kind of talked about the graphs and all that, but we didn't go into it as much detail as we have. So we're talking increasing, decreasing, and then we're going to be looking at local max and mins. Remember the EBT we looked at only what kind of max and mins? Absolutes. So that's the difference between this. This is a polynomial graph. It's a little cut off. You can just kind of pretend it's not. Okay. I don't think, again, check this out. F is continuous on a closed interval, differentiable on an open. Pretty standard operating procedure. Okay, if f prime of x is greater than 0, that means positive, right? What is going on with f? It's increasing. F prime is negative. F is decreasing. Okay. Rarely do we talk about f prime increasing and decreasing. We could, but we don't. It's kind of confusing because we think increasing. So this is really pretty important to know. Okay, so I got a graph of f prime, and I can figure out my equation of f prime. 2 different things. That's why this line is here. These are 2 different examples. Okay, so if f prime is sitting here looking at us, we want to know where is f increasing and where is f decreasing, okay? From the graph. Now, what they don't want you to do is try to graph the derivative. If that's all you want to know, you're good. Okay, f increasing, what's going on with f prime? Positive. Okay, so highlight the positive pieces of f prime. So I think it's positive here and here, correct? All right, so what intervals am I talking about? Let's just say, that's -4 right here. We'll just, we'll go for 0. And let's say this is 5. Okay? We could spend more time figuring it out, but that's good. All right, so where is f prime positive? From -4 to 0, and then again from 5 to infinity. Yes, we don't know any better. We know I told you it was a polynomial, so you're assuming we've seen the rest of the graph. Typically, we're just looking on an interval, so watch that. They may say on, -10 to 10, and then you'd stop at 10 here instead. But right now we're good. All right, decreasing, that means what's going on with f prime? It's negative, so that's this piece, and then this piece. Okay, when you're estimating, if you're estimating, you need to estimate, you need to be consistent. So now say, okay, I'm going to go from -infinity to -4. That needs to match that number. Okay, and then again from 0 to 5. That's the negative part. Okay, so that's what you do if you have a graph of f prime. Okay, we did that a little bit before. All right, we haven't done very much of this. So again, it's the same concept, but we have to figure out f prime. So let's figure out f prime. What is it? Jessica. Very good. Okay. Now, I need to know this again. Where's f increasing? Okay. Where's f decreasing? That's what I want to know. Where is f increasing? Where is f decreasing? Okay, so I need to look at where f prime is positive, where f prime is negative. Okay, so how do I do that from our equation, 3x squared minus 5x minus 2? So you want to do greater than, and then you want to do another one that's less than? Is that what you're telling me? Well, that's a fabulous idea, Madeline. We can do interval testing. You have two choices, really. You basically are going to start with equal to 0, because that's going to where it separates. So you're going to say, where is it equal to 0? And then you can graph it, or you can interval test. Or you can do a combination of both, which is kind of my personal favorite. Okay, so we got this graph, factored, I mean. What do you think? Are you all done factoring yet? I don't think so. Not with that -2. Thank you for trying.
Oh, nice saving.
Okay, that'll give you -5 because you get the -6 and the +1, and then the -2 as well. So x, if it was equal, would be what? -1/3 and 2, right? Okay, so I'm going to pull this all down here. This positive. All right, we have -1/3 here and 2 here. Now, those are, if we were graphing, those would be called our what? Our zeros. Okay, do you know that this is what this graph is? It's parabola. opens up. So this is what it looks like, ish. I don't care how far it goes down. I know it's going to start up, going to hit so negative 1/3, going to come down, going to hit the 2. Okay, so my interval testing that I would do is I would plug in something over here, and I would say f prime is positive over here, right? It's also positive over here because I know it's above 0. That's positive. And then down here, I would see, oh, that's negative because it's below 0. Okay? Now, I like to write f prime, because, and you'll see here probably more, instead of just plus, minus, plus. Okay, I like to write f prime so that we know exactly what's plus, minus, plus. It's f prime. Okay, because the words f prime is positive, then we know, oh yeah, f prime is positive on the interval. We'll just assume infinity, so negative infinity again. So to negative 1/3, and then again at 2 to infinity. Okay, and f prime is negative from negative 1/3 to 2. Okay, a lot of quadratics will come up on this type of problem, and you have a lot of experience with excuse me, graphing quadratics, so you should be quick to do the interval testing. If it was a cube that you were like, I don't know what that looks like, then you would have to interval test. You check out a -2 maybe, or a 0 and a 5, and then you're good. Okay, it'll serve the same purpose. Okay, if you know the graph, it's quicker to do the graph. All right, sometimes we don't. Any questions on that technique? Increasing, decreasing. Okay. All right. Let's talk about this first derivative test. Now, the test is for local extrema. I just want to make sure I use that word because sometimes it's like, what does that even mean? That's the plural of extreme. Yes. True story. Extreme. Yeah. All right. So when you say let's do the test, we're testing for local maximums. Okay. All right. So again, f is a continuous function, and c is a critical point that we found before too. All right. First thing is, if f prime changes sign from a positive to a negative at c, then f has a local maximum value at c. Yes, I would write that down. Okay. F prime changes the sign from positive to a negative at c, then f has a local max. Let's think about this. Let's say f prime looks like this to this. This is positive f prime. This is negative f prime, right? That right there is a local max. That's what that means. F prime changes from a positive to a negative right there. Okay, F prime. All right. If it changes from a negative to a positive at C, then it has a local min. Okay, so we go negative, F prime is negative, to F prime is positive. This point is a local min. Okay? Remember, that's your C. Those are your critical values, the only ones we're considering. You can't check it's only going to change at the critical values. If F prime does not change signs, then there's no local extreme value at C. Okay? So, when F prime changes signs, there's something happening. There's a local max or local min. We do not. We would only know if it's an absolute. That's a very excellent question. Did everybody hear Sophie? She asked do we know if it's an absolute? We only would know if it's an absolute if we checked it out and said, okay, that's the biggest one or that's the smallest one. That's the only way. That's the only difference between absolute and local. Okay. All righty, I think there's an example at the bottom of the page. Sorry. You can dive in if you want, if you're ready. Find the local extreme values of F. And then, of course, we're going to find increasing and decreasing for F. Remember, we don't really care if F prime is increasing or decreasing. We're talking about F. We're talking about increasing or decreasing. But remember, don't say it. Just say F of X is increasing. All right, is everybody ready? Okay, so I'm going to find my local extreme values of F. I'm going to start with F prime. Very good. Now, what is it? Very good. Okay. If I'm going to do local max or minimums, I need to find where they change signs. So I'm probably going to do some interval testing. I'm going to start with where it equals 0 because those are going to be my critical values, right? So find derivative, find critical values. Anything in? Okay? So critical values is when the derivative equals 0 or does not exist. Is 3x squared minus 12 ever going to not exist? No. So we're going good. 3x squared equals 12. X squared equals 4. X equals plus or minus 2. Okay. Notice another thing that is different from extreme values is they don't give us a certain area to look at. They just say, just do it. The absolute, they give us like an interval to look at usually. Yes, no. We looked at both. Yes, you're supposed to. Yeah. Yeah. We did look at where both critical values are where F prime equals 0 or where F prime doesn't exist. Okay? Yes.
I thought you said the extreme values and absolute, like extreme maxes or absolute maxes. Yeah.
Local? No, I said that like an absolute max could also be called a local max.
Right.
But so you're going to have several local maxes usually, and then one is going to be the absolute max.
No, like that. But what is the difference between an extreme max and an absolute?
Okay, wait. An extreme is
Not a max or a min.
an extreme is a different word for absolute. Or
That's what I thought.
no, stop. No, it's not. Extreme values are max and mins. Extreme values are max or min, either local or absolute. Extreme does not mean absolute. Extreme values are either local and or absolute max and or mins. So extreme value is another name for local max or mins
So
or absolute
when it
max.
says local extreme values, you're finding local max and mins for this problem.
Correct. Correct. Yes. Yes.
Okay.
Local max for mins. Yes, that's good to clear that up. Okay. All right. So we have critical values right there. All right. We don't have to worry about an interval. Question?
Yeah. So I know when we're finding it, when prime doesn't exist,
Okay. We talked about that. Remember, we said that's not going to happen.
but on the also FMX and F prime.
No. You just looked at f prime of x equals 0 or f prime of x doesn't exist. So the critical values, Eo. For the critical values. Okay? All right. So now what? Interval testing? Okay. All righty, here we go. And this will be good for increasing and decreasing. Then we've got all that data too. So we're going to split it -2 and 2. Is this quadratic? So then it's going to open. So we can, you don't have to do that. It's just a visual. So what's that prime going over here? It is positive. Over here it's and positive again. Okay, so we got everything we need. At -2, f prime changed from what to what? Positive to negative. So what does that mean? At x equals -2, that is a not absolute, local x. Okay? This whole dot thing, therefore, Kate, you like that, right?
I do.
Yeah, me too. Okay. At x equals 2, f prime changed back from, it was a negative and then went across to 2, it went to positive. So therefore, x equals 2 is a local min, change from positive to negative. Okay? I'm sorry, negative to positive. All right, positive, negative would look like this. That's a max. Okay. Increasing, decreasing. That's a piece of cake because we got all the work done. So F is increasing. Where? Sorry. Negative infinity to -2 and what? Okay. F is decreasing. -2 to 2. Done. Okay.
So the thing in the red, that's what you're really looking for this problem.
Well, we were looking for find the local extreme values, which is this,
So it's
and we were looking for this. Yep. Okay. Yes, I mean,
You're right. Bigger red circle, those things.
Mhm.
Those, when you said it's a local max, you mean on alphabetics, right?
yes, yes. So if you looked at, thank you for clarifying that. Let's do this because we always probably should take the time more than we do. I'm just going to look at x cubed. I'm looking at f of x here, minus 12x minus 5. Okay? I'm going to look at the graph. I think I have a standard graph in there now. Okay.
well,
I know then.
special.
That was bizarre. Okay. Because there was supposed to be something happening at -2, wasn't there? Okay. I'm going to just clear this out. Ah, I forgot my x. That's what happened. I just saw it after I cleared it. Minus 12x minus 5. Oh, for gosh sakes. Let me, okay. Let's see if that works better. All right, so polynomial, I know it's getting cut off. Okay, if you want to get our y a little bit bigger, let's do -20 to 20, that should cover it. Okay. There's your max, there's your min. Almost didn't cover it, but okay. But yes, very good. Good thing to come back to. There's your local max. Right here. Local min right there. Okay. Now, is there an absolute max and min? Right. It's not a, see, because this is just going to keep going bigger, 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 and saying this smaller, smaller, smaller. So that we have to say, okay, I'm going to look at this spot. What's my absolute biggest spot? What's my absolute biggest, smallest? To get a local, or to get an absolute. Okay? Any questions? Thank you for saying that, Abby. It's a good visual. It's good to remember what we're doing here. Anybody else? All right. Okay, concavity. We haven't spent a lot of time on concavity. We got concave up, we got concave down. Remember that? Okay. The second derivative test, you remember that we used to determine concavity? Okay. Concavity is going to be just like concavity. Here's an analogy. Concavity is to f double prime as right. So it's going to be, and here it says, I don't like this. It works. I don't like it though. And we talked about this pretty seriously when we did it. Concave up if F prime is increasing. Okay, I don't really like to talk about F prime being increasing. I like to talk about F double prime being positive. But that's the same thing. Okay? So it just depends on what you want to look at. Remember, if you're looking at function, let's look at that last one kind of-ish. Okay, F prime. Now, if we're comfortable with concavity, we would say this is concave probably about right here. From here to here is concave down. And from here to here is concave up, right? Concave up, concave down. Just a blanket kind of thing. Okay, so if you do, this is F, not F prime, just so you know. Okay, if you do your tangent lines, all the way to here, what are they doing? They're getting, they start out really steep, they get less steep, they get less steep, they get 0, and they're decreasing, right? Until we get to here, and then they start, wait, we're going to start getting bigger. Now, I don't like that. I don't like increasing and decreasing. I like this. But you can do it. It just gets confusing. But let's try the concavity test with this example, and you'll see what I mean. Okay, this is one we've already done before. We already said, remember Jessica gave us F prime was 3x squared minus 5x minus 2. Remember that? Okay. We want F double prime now. What's F double prime? 6x minus 5. Okay, so concavity, if we want to do, we want F double prime is positive, concave up. And remember, we're talking about F being concave up. It's really not right to talk about F prime being concave up. That's just weird and wrong. Okay, concave down, weird and wrong. Yes. Okay, so we're going to do the same thing. We're going to interval test on here. We're going to start setting it equals 0. Okay, 6x equals 5. X equals 5, 6. Okay, interval test, 5, 6. All right. Now, it's a line. That's your 0, but it's weird because we don't do lines, but so you might want to think about just interval testing 0 and 2, okay? If I plug in a 0 to 6x minus 5, is it going to be positive or negative? I heard positive and negative. It's going to be negative. 0 minus 5 is negative. So I'm going to do 5 double prime is negative. Okay? Then I don't say, what's negative again? 5 double prime. Second derivative. And then this is going to be, what are you laughing about now? Have I done said something stupid again?
You just have a 5 double prime.
Oh, gosh. Sorry. F double prime. My brain is a little foggy. Okay. All right. So tell me where F. Notice I almost said it, but I changed my mind. Where is F concave up? 5, 6 to infinity, because that's where F double prime is positive. Very good. Where is F concave down? Okay. Now, did we have this graph, right? That's the same one? All right. So, 5, 6 is what? About right here? Is that a reasonable place to switch our concavity around? Yes, it is. Oh, that's a good point. Haha. Inflection points. Okay? The inflection point is where the concavity changes, and it can change either way. It can change positive to negative, negative to positive. Okay, and yes, it's usually an ordered pair. If you're really feeling kind of like, I'm gonna try this. You could say at x equals 5, 6, that would be totally fine for the most part. Okay? If you're looking for an ordered pair, then 5, 6, where are we gonna find the y of this? Plug it in where? Yeah. Your f, right. The f of 5, 6 is what we want. So we get a calculator, we're just gonna go for it. Second value, 5, 6, negative, what is that? 14.4213? 4213. Okay? Got it? Yes. Yes. Okay, any questions on that? So concavity is just, we're just looking at positive and negative. We don't have to talk about inflection point is just where it changes. You all remember that? Good job. Here we go. What?
That's not even as bad as what I thought. Oh, that was terrible. It was so traumatizing.
I know.
Okay, is that
I remember that
order
story.
pairs where it's like 5, 6, comma, and decimal? Are they gonna be like? That's shitty?
3 decimal, you're good. No.
So it
No.
doesn't matter if it's mixed.
No. That's a good question. But honestly, don't do any less than 3 decimals because they won't count right. It's an accuracy thing. They're really weird about it. Okay. All right. I think we covered this. Let's go on and do talk about a second derivative test. Again, this is a different test for local extrema. Now you're going to say, I'm going to use the first derivative test because it makes sense to me, because I've been using it, I'm good. Sometimes they will force this by only giving you certain information. So just be aware of it. Okay, second derivative test for local max and min again. Yeah.
Everything you just did.
Yeah. The first derivative test was this. Find the critical values, and then do interval testing if it changes from positive to negative, negative to positive with the local max. Okay. That's all right. Second derivative test. Here we go. Okay. We're using the second derivative to test the critical values. We're still going to find the critical values. Okay. C is still a critical value. See? Right here, look. C is critical value. Okay. So we're going to do the same thing. We already found critical values for this, didn't we? Just going to use a different test. So we do, if we were starting over, we do this. Okay. And then we do the second derivative. Right? Okay. We already found the critical values. What were they?
But the equation was different last time, wasn't it?
Well, we did this one, didn't we?
The equation last time.
No, I know, but we did that one. I think it was down at the bottom of this page.
Oh, we did.
Yeah.
Plus minus.
Critical values plus or minus 2. That's good. All right. X equals plus or minus 2. Okay. Previously found. All right. So here's how the second derivative test works. It's honestly kind of nice if the second derivative is an easy thing to find. If it's not, then it's like, meh, I'd rather do interval testing. But this is really quick. We found this. We found the critical values. Then we found the second derivative. Okay? So pretty quick. We don't do interval testing for the second derivative test. That's the first derivative test. Okay? The second derivative test says this. Plug in the critical points, to the second derivative. Okay? That's what this means. F prime, that's what this means. We're plugging in the critical points right there. Okay. We're really just interested in positive or negative, but it's an easy one. We can get it. This is 12 and this is negative 12, right? Okay. Now, if F double prime of C is greater than 0, this is definitely greater than 0, right? That means this x equals 2 is a local min. Okay? So that was a lot quicker than doing all that interval testing. So if all you want to know is local max or min, this is your test, again, if the second derivative is easy to find. Okay? Negative 12 is less than 0. What does that tell us about this? That x equals negative 2 is at a local max. Now, it seems backwards, but remember, f double prime is concavity. So if this is concave up, think about that. Because we have a max, that's why we have to have a local min. And if it's concave down, we're looking at this, so that's why we have to have a local max. Okay? So it does make sense if you think about what concavity tells us. Okay? Don't remember. Max and Ruby, yes. Anyway. Okay, I think these are wrong. I think this is from a previous problem. So, all right. Anyway, go back. Like your life, Max and Ruby?
She was so lost.
All right. And points of inflection. It's the same problem. Where did the concavity change again? Did we figure that out? 6x, which is the double prime is f double prime, not 5 double prime, right? F double prime is 6x. Where does the concavity change? At 0, okay? Because I know 6x equals 0, x is going to equal 0. I'm just solving it. Okay. If I need it to change, I'm going to find 0 because one is going to be positive, perhaps, and one's going to be negative. So at this, I could plug in negative 1. What's 6 times negative 1? Okay, so my double prime is negative, right? Over here, what's my double prime? Positive. When my concavity changes, there's an inflection point. So what's my inflection point? Inflection point, or some people call them point of inflection. 0 something. Where am I going to get that number again? Original function. So it's negative 5. Right? Remember, the points of inflections are on that graph of f. We'll plug them into this. So it's not going to give you an ordered pair on your graph. Okay? I usually call them IPs, but you will have people that refer to them as PIs. Okay? Let's do this one. I know we're running out of time. Okay. So let's have fun. Just cosine, okay. What's f double prime? Just in case you want to use it. Okay. We are on max. Concavity is going to equal 0, right? So where inside of x equals 0? Notice what I did. I took out the negative. Here's my beautiful.
Oh, it's 0, 0.
Where's sine x 0? Here, here, and here on this interval, right? So where's the positive? Be careful, because I did the negative, I'm really looking at the graph of this, right? Okay? So anyway, we'll stop at 49.